Hello grade 12s. Welcome to another online lesson of AP Mathematics, and today we're going to be discussing mathematical induction. Now, mathematical induction is part of chapter 1, so it's part of your algebra chapter, which means this does not have anything to do with calculus. Now, we're just going to quickly have an overview of what mathematical induction is, and then we're going to go and work through as many examples as possible, because I find that mathematical induction, because it is quite theoretical, but also very procedural initially, people look at it and they go, I don't understand. So yes, I think once I go through what mathematical induction is and what it entails, you might also go, I don't understand. And it's only after about the fourth example that you suddenly look and you go like, oh, but this is actually quite easy. So this is why I am going to go and I am going to explain what it's all about, but I'm also going to do lots and lots and lots of examples just so you can get a very good idea of what mathematical induction is. Right, so first the overview. Mathematical induction is used to prove a rule relating to sequences and series. So we have quite a few rules relating to sequences and series in core mathematics. For instance, we have the formula for calculating the sum of a geometric series, and we have a formula for calculating the sum of an arithmetic series. Now, you can then use mathematical induction to prove that that rule is in actual fact true. So not just go and use the rule, but show that it will always hold true. The other place where you can use mathematical induction is how to prove that, and this specifically it says can also be used to prove divisibility, but you'll see just now when I discuss the two types of mathematical inductions, I will state that it's about proving that an algebraic expression is divisible. Okay, so that proving divisibility is the divisibility of an algebraic expression. But like I said, we'll get to the examples and the types just now. Now, first things first, we have to talk about the fact that this is a formal mathematical proof. And because it's a formal mathematical proof, you cannot go and follow your own steps. You cannot be creative with this. Unfortunately, this is very, very strict on how you present the proof. It's got very clear steps, and if you do not follow these steps, then it's not mathematical induction. And you'll see in all of the examples that they give you, they state very clearly using mathematical induction. So because they say using mathematical induction, you have to use this mathematical proof. So very, 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 very important. Do not make up your own steps. Follow these. So I'm going to go through the steps first, and after I've gone through the steps in the examples, I will refer back to them again and again so you can see exactly what it entails. So step 1 says, prove the formula works for the first term, usually for n equal to 1. So this is, and in the textbook they also say, this is a lot like dominoes. Now dominoes, I'm talking about the fun dominoes. I'm not talking about the dominoes game that you play. I don't think anybody's really ever played the game dominoes. I surely haven't. I'm talking about when you stack dominoes in a row and you keep stacking them. And then what you do is you push over that first domino, and the first one then makes the second one collapse and so forth. And it causes a chain reaction pretty much. So that's what we're looking at. We're looking at a chain reaction. So that first step says, prove the formula works for the first term, usually for n equal to 1. And using that idea of dominoes, if I want to get these dominoes to fall over, I have to push over the first domino. So that means if I can push over the first domino, it means we have at least the opportunity of this chain reaction taking place. But if I can't even push over the first domino, then it's not going to knock over any of the other dominoes. So logically speaking, it won't work. So that's why first we have to show that it will work for the first term. The first domino will get pushed over. Secondly, we've got to prove that the formula holds true for 2 consecutive terms. Now, this again, talking about the dominoes, says, if I don't look at like the first or the second domino, I go down the row. So imagine there's lots more dominoes. I was obviously just too lazy to draw more. But say, for instance, there's like 100 dominoes. And I do a quality check somewhere in the line of these dominoes. So I go, for instance, to the 70th domino. And I look at it and I go, let's assume that that domino will get pushed over. Will that domino, if it gets pushed over, knock over the next one? So that's my quality check. So that's why they say prove the formula holds true for 2 consecutive terms. And those are any 2 consecutive terms, not necessarily the 70th one that I used as an example there. So in order to do that, This is exactly like I said, assume it's true for n equal to k. So assume, in this example that I gave you, the 70th domino will get knocked over. That's an assumption, but we're assuming it will get knocked over. And then prove from this assumption that you made that this one getting knocked over will then knock over the next one. So prove from assumption it is also true for n equal to k plus 1. So if I assume the 70th domino is going to fall over, will it then knock over the 71st domino? So that's what I'm trying to prove, is prove it holds true for 2 consecutive terms. Then lastly, if I can prove that it will knock over the first term, so it's true for the first term. So in the terms of dominoes, the first domino will fall over. And if I can do that little quality check saying that if the 70th one knocks over, it'll knock over the 71st one, then I can also make that statement over here. I can say the first one will fall over, but based on this any 2 consecutive terms that I've proven. That means if the first one knocks over, it will knock over the consecutive one, which is the second one. But then the second one gets knocked over. So if the second one gets knocked over, that will knock over the next one, the consecutive one, which means it will knock over the third one. And then the third one will knock over the fourth one, and the fourth one will knock over the fifth one. And this chain reaction will continue indefinitely, into infinity. And this is how the process of mathematical induction works. And that's why your last step is always your conclusion. Your conclusion is saying that if the first term is true, if it works for the first term, and if it works for any 2 consecutive terms, in this case, if it works for the kth term, and I know that's a little bit weird to say, but the kth term meaning any term in that sequence, so if it proves true for that term, then prove that the next one also knocks over. Then I know that it will knock over everything. So this might now be a little bit iffy in your head, and you're going like, okay, I get the dominoes, but I don't actually get this. So once we start doing the examples, hopefully you'll see exactly how it works. Right, so let's jump straight into the examples. The first example is in your textbook, and this one is one of the type 1 examples. And type 1 is going to be rules relating to sequences and series. So as I said before, we're going to get the ones relating to sequences and series, and up top I also said we're going to get the ones relating to divisibility. So I consider type 1 to be the ones relating to sequences and series. So in the textbook on page 13, example 1, it says, prove the sum of the first n natural numbers is given by that formula. So let's just first write it out. So what they're saying is the first n natural numbers. Now the natural numbers start at 1. And they're saying the sum of these natural numbers. So 1 plus 2 plus 3. And then I'm going to skip a few going up to n, because they said the sum of the first n natural numbers. So that's the sum of the first n natural numbers. And they want you to show that this will be equal to that formula. So n times n plus 1 over 2. So sometimes they're very nice. Sometimes they write that out for you, which means it's much easier to use. You'll see later in some of the other examples they don't write this out, so you might have to create this statement first before you can jump into the mathematical induction. So in this case, we first had to create the statement. Right, so now we have to follow the steps. Now, first step is we're going to prove that the first domino gets knocked over. I know I keep on referring to dominoes, but the dominoes actually help quite a lot to understand the steps. But the proper way to state the step is to say, we now first have to go and show that it is true for the first term. Now, in order to prove it is true for the first term, I'm going to write it out. And this you have to write out when you do the example. So you have to say, for n equal to 1, showing them that you are talking about the first term. Now, in order to prove it's true, we cannot use that statement of equality. We've got to prove that statement of equality. So you're going to split it up and you're going to say on the left-hand side, take only the sum of the first term. So obviously the sum of the first term is then just equal to 1. So that's 1. Then we're going to go and we're going to say on the right-hand side, use the formula for the sum of the first term. So that also just means if we only use the first term, so if n is equal to 1, then I can go and I can say, let's substitute in with 1 over there. So 1 times 1 plus 1 over 2, and this is going to be 1 plus 1 is 2, 2 times 1 is 2, 2 divided by 2 is 1. So therefore, I can now go, and it's very important to show these conclusions, therefore, it's true for the first term. So true for n equal to 1. There we go. So that just means that the sum of the first term on the left-hand side is going to be equal to the formula of the sum of the first term on the right-hand side. Now, I find that a lot of the time people look at this and they go like, okay, that was pretty easy to do, but what is it you are actually doing? So I'm going to just write here in a little bubble, and this is not part of the sum, but in a little bubble, I'm just going to show you what it is that I'm actually doing. So what it is that I'm actually doing is I'm showing in this particular step that T1, the first term, is equal to S1. So I'm just showing over here the first term, which is 1, is equal to the formula for the sum of the first term. It sounds silly to say the sum of the first term, but this is what I'm trying to prove. That's the first step. Right, now what I need to do now is that's step 2. And this step 2 is twofold. We have to first assume that it's true for n equal to k in order from that assumption to prove that it's true for n equal to k plus 1. So we're going to write out assume for n equal to k. Now, because we are assuming it's true, I'm not going to split it up in a left-hand side, right-hand side like I did up top here. Because here we're trying to prove that it's true. Here we are assuming it's the truth. So all this step entails is I'm going to go and rewrite this exact same statement out. So exactly what I wrote there. But now, instead of having n over here, and over here, I'm going to substitute it with k. So I'm going to say, assume that 1 plus 2 plus 3 plus skip a few plus k is then equal to k times k plus 1 over 2. There we go. So I use the statement of equality because I'm assuming this is in fact true. Now we have to go and say, but if this is true, will it then go and knock over the next one? So the next one, the consecutive term after this one, is for n is equal to k plus 1. Now, this one is where people normally get stuck, where they go like, ooh, I think I know what's going on, but I'm not exactly sure. So what you are going to do is you're going to do the following. And hopefully, if I write the little bubble again over here, so please note the bubble is not part of the sum. The bubble is just explaining what I'm doing. So over here I wrote that term 1 plus term 2 plus term 3 plus all the way till term k is equal to the sum of k terms. This is what I've written out over here. Whereas now what I'm trying to prove is I'm trying to prove that the first term plus the second term plus skip a few plus, and we're also going to take that k term, which is something I used over there, but now I'm going to add on the next term. So I'm going to add on the next term on the left-hand side, meaning over here, you'll see just now, I'm going to add on this side, is equal to, and now be very, very careful, because a lot of people, they will just go and say, oh, so this is the s of k plus 1. You can't write the s of k plus 1 because that is what you are trying to prove. And please remember, you cannot use what you're trying to prove. So I'm trying to prove that the sum of k terms, which is this one, plus the next term. And this is why, people, you are allowed to use this statement of equality in this sum. Because all I'm really doing is I'm taking this part, which I've assumed is true, and I add on the next term on the left-hand side, and I add on the same term on the right-hand side. And remember, if I add the same term left-hand side, right-hand side, then of course it's going to be true. So I can keep using that statement of equality. But what I'm then trying to do over here is I am now going to have to simplify this, and I'm going to simplify this in order to prove that this is in actual fact equal to that k plus 1. So please remember, we couldn't use it over here, but we're going to try and prove it. So again, I'm putting this in the bubble so that when I do this particular step, you can see that this is in actual fact what I'm trying to do. Okay, so for n is equal to k plus 1, I will then go and say it's 1 plus 2 plus 3 plus, skip a few, and I go to k. But now I'm going to add on the next term. So in this case, the next term is going to be k plus 1. So that was this t of k plus 1 that I've added on. Now, it might be a little bit confusing, and the reason it's a little bit confusing is the actual term k plus 1 is equal to k plus 1. In the next example, the term k plus 1 won't be equal to k plus 1. Hopefully, then it'll be a little less confusing. But I'm going to do 2 more examples of this one specifically. Then I'm going to state that it's equal to this one, which, as I said, is the sum of the first k terms. So k times k plus 1 over 2. I'm not using the s of k plus 1 because that's what I'm trying to prove. And remember, you can't use what you're trying to prove. And I will just add on exactly the same thing on the right-hand side that I already added on the left-hand side. So this is just the part where I said that one is the sum of the first k terms, and I'm just adding on the next term, which is the t of k plus 1. Now, I want to prove that this right-hand side, and that's very important in these particular examples. I'm not going to mess with the left-hand side in this step at all. So just on the right-hand side, I want to go and I want to simplify that right-hand side. And I want to simplify the right-hand side until it is equal to the sum of k plus 1. Now, this is why we actually have a little cheat here. And this little cheat, careful, 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 is I know what my answer's got to be. And the reason I know what my answer's got to be is my answer, I'm going to put it down over here, has got to be equal to this formula, but not for k plus 1. So if I look at this formula, then I can actually just quickly go and I can substitute k plus 1 in there. Now, if it gets a little bit confusing, you could also refer to this formula. This is the formula that needs to have the k plus 1. So I know it's going to be equal to, over here, n, or k plus 1, times n, which is then k plus 1, plus 1 over 2. So I now need to take this right-hand side, and I need to go and simplify it until I get to this. Because if I can simplify the right-hand side to this, then I've proven this. I've proven that the sum of the first k terms plus the next term will be equal to the formula. Because remember, that's what I'm trying to prove, the formula of k plus 1 terms. Right, so in order to simplify this, I need to go and I need to add fractions. So I need to get an LCM of the denominator, which is then 2. This is already over 2, so I've got k times k plus 1. And now you'll note, a lot of the time, I'm not going to expand this. And you'll see just now why it's not a good idea to expand. Now, this particular one is supposed to be over 2, so I need to multiply the top by 2. So I multiply 2 times k plus 1, and this is going to then be put over 2. Now, hopefully, you will notice why I didn't expand, because up top, I can factorize and take out k plus 1 as a common factor. So I take out k plus 1 as a common factor, and then I'm left with k plus 2. And now, hopefully, you guys will see that this is algebraically equivalent to this. Because there's my k plus 1 that I was looking for. That k plus 2 can be split up into k plus 1 plus 1. Which means I have now proven that the sum of the first k terms plus the next term, and please understand, to add that next term, I used this formula for the next term. I didn't use the formula for the sum of the next term because that's what I'm trying to prove. And again, I can't use what I'm trying to prove. Okay, so I added the next term and then I just simplified it until I got to this. So I'm not going to put the bubbles in the next one because I know sometimes the bubbles seem a little bit confusing, but I am going to refer back to those bubbles. Hopefully you'll understand. Now just the last step, and people, if you don't do this last step, which is your conclusion, you will actually lose 2 marks because the conclusion is the easiest 2 marks of the entire sum. Now I always joke and I say to people, when you do the conclusion, I say ink it, stamp it. And the reason I say ink it, stamp it is simply because the conclusion is always the same. So, conclusion. And again, this is worth 2 marks, so please do not skip it. So you can then go and say, therefore, by the process of mathematical induction, I've proven, sorry, let me move this up. By mathematical induction, I have proven that it's true for n equal to 1. I've also proven that it's true for 2 consecutive terms, meaning if it's true for n equal to k, it'll be true for the next one. So that means if it's true for the first term, then it's also true for the next term. So it's true for n equal to 1, n equal to 2, n equal to 3, and those are the dominoes that keep on knocking over. So true for n is an element of the natural numbers. But they're very, very pedantic for you to say by mathematical induction. You'll see just now in the next example, I'm actually going to shorten this conclusion. But, and I'll show you the shortest possible version you can write and you can still get your marks. But you have to state that by mathematical induction, it is true for, and then you just have to show that it's true for the first term. And then because it's true for the first term and it's true for each consecutive term up here, it'll be true for the next one and the next one and the next one. So it'll be true for all your natural numbers. So I know I'm going super, super slow. The next one, I'm going to speed it up. And hopefully when I speed it up, you guys will get a better idea of what it is that we are doing. Okay, so this was the 2019 IB paper, and they asked in question 2, use mathematical induction to prove that the sum, sigma, of I equal to 1 to n of that expression 2 to the power of I is then equal to 2 to the power of n plus 1 minus 2. Now again, like I said, they haven't written it out quite nicely. So I need to write it out showing on the left-hand side, I'm adding the individual terms. And if I add those individual terms, it will be equal to this, which is the sum formula. So this sigma notation shows me adding the individual terms. And I can do that by just putting 1 into I. So 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3 plus, skip a few, all the way to 2 to the power of n. Must then be equal to this sum formula that they've given me, 2 to the power of n plus 1 minus 2. And this is what I'm trying to prove. I'm trying to prove that if I add the sum of the first n terms, then it's going to be equal to that formula. So let's go according to the process of mathematical induction. And we're going to start with the first term. So we're going to say for n equal to 1. So left-hand side, right-hand side, because please remember, we're trying to prove this is true. This is not an assumption. We need to prove this is true. So I just take the first term over there, which is equal to 2. And then into the sum formula over there, I sub 1 in. So I'm going to say it's 2 to the power of 1 plus 1 minus 2. And that's going to be 2 to the power of 2, which is 4, minus 2 is then 2. So left-hand side is equal to the right-hand side. And the formula is true for the first term. So that's that first thing, knocking over the first domino. I know that it'll be true for the first term. Then I move over and I say assume. So I'm assuming that for some random term, k, that this will be true for that random term k. So all I do in this step is I write this exact statement out again and I just substitute in with k. So that exact statement, skip a few, 2 to the power of k. I've forgotten to put the k in there. So substitute k in there is equal to 2 to the power of k plus 1 minus 2. There we go. And we are using the equal sign. Why? Because we're assuming it's true. Now we move on and we say for n equal to k plus 1. So this is the next term, the consecutive term, meaning the term that follows on from here. So from the one that follows on from here, I may need to now go and use this formula to get the next term, or the k plus 1 term. And I will add it on the left-hand side and the right-hand side. So that's what I'm doing. And please remember, I'm not going to sub k plus 1 into this formula because this is what I'm trying to prove. Okay, so first I'm going to go and say 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3, skip a few, plus 2 to the power of k. So the next term that I add will be 2 to the power of k plus 1. Then I'm going to use this exact statement that I've got over here, so I just carry it down. And then whatever I add on the left-hand side, I need to add onto the right-hand side. So the exact same thing. So 2 to the power of k plus 1. There you go. So I add that exact one on y because then I know the left-hand side is equal to the right-hand side because I've just added the same thing on there. Now, if you're getting confused, just to remind you what we are doing, we are going and we are saying that we are taking this step, so assume true from n equal to k, and I'm just adding the next term. And I'm adding the next term to the left-hand side and the right-hand side. And now what I want to do is I want to take that right-hand side specifically, and I want to simplify it until I get the formula for that k plus 1. So again, I'm going to write down right-hand side is equal, and I know what the answer has got to be. So I'm going to cheat a little bit, I'm going to skip a few, and somewhere around about there, I'm going to write the correct answer just so I know I've gotten there. And that correct answer comes from over here. I want to prove that this formula is true, the sum formula is true for k plus 1. So I'm going to write 2 to the power of k plus 1 plus 1 minus 2. So all I've done is I've substituted k plus 1 into this formula over there. Because I know if I can get that answer, specifically k plus 1, then I know that the sum of the first k terms plus, where did I get that? Sorry, here. The sum of the first k terms, which is over there, let me just write that down again so you can see. So the sum of the first k terms plus the next term. I'm trying to prove that this is equal to this, which is the sum of k plus 1. Again, people, this is not part of the formula. This is just to explain what I'm trying to do. Okay, so I need to simplify this. In order to simplify this, hopefully, I'm really hoping you guys are noticing that these are like terms. They're like terms. It's 2 to the power of k plus 1, and it's 2 to the power of k plus 1. So I can add them, and I can say there are 2 of those 2 to the power of k plus 1 minus 2. There we go. Now, if I multiply these two, because the bases are the same, I can then go and I can say it's 2 to the power of 1 plus k plus 1 minus 2. And hopefully you'll notice that this is now exactly equivalent to that. So I've actually left too much space here because this is now equal to that. So I've proven by means of mathematical induction that this formula is in fact true. So now I can go and I can write my conclusion, which I can say, therefore, by the process of mathematical induction, true for n an element of the natural numbers. And that's the shortest way you could write it. You can then just go and say, by mathematical induction, true for n an element of the natural numbers. But please, people, they give you 2 marks for this conclusion. Do not forget it. Right, so I will continue in the next video doing one more example on this particular type, and then I'm also going to do 3 examples on divisibility. But hopefully by now you're starting to realize it's actually not that difficult process. So the next video will just be titled Mathematical Induction Part 2.